Hi everybody, welcome to our first two tests to see if series converge or diverge. So you may remember in the last video we talked about how what you should expect on the next exam will be a whole bunch of series, and the question will just be, do they converge or diverge? And of course you have to explain why, right? You can't just put, yes, I think it converges, but you have to explain why, and usually that boils down to some sort of a test. So the two tests we'll talk about in this video are the divergence test, which in some ways may be the most important of the tests, and the integral test, which may be the least important of the tests, but there are times when only that one will do. So let's jump right in. Divergence test. Okay, this is probably the most easily misunderstood test, but again, it may be the most important. And it's really easy. If the sequence that you're adding up, remember a series is a sequence added up, right? If the sequence that you're adding up doesn't converge to zero, then the series has to diverge. So let's listen to that again really carefully, because again it's super easy to misunderstand what this says and to think it means more than it really does. If the sequence we're adding up does not go to zero, so that could mean that it goes to something else like 7, or it might mean that it just bounces around and oscillates and never converges, or that it might go off to infinity. But if it does anything other than converge to zero, then the series must diverge. So a lot of times when I'm doing this, like in a live class on the board, what I'll tell students is take your thumb. Now, of course, I don't have a thumb; I have a blue pointer here. But take your thumb and put it over the sum, right? And look at the sequence that's left. And if that doesn't go to zero, the answer is we diverge and we're done. Right? Let's look at an example or two. So here's the sum of k over 2k plus 1. So the sequence that I'm adding up is k over 2k plus 1. So let's check and see, does that sequence go to 0? Well, okay, it's really easy to tell, because remember from the tower of power, I got a k in the top and a 2k in the bottom. The k's match power-wise, they tie on the tower of power, so the answer is a half. This sequence converges to a half, and of course a half isn't 0. So the sequence we're adding up converged, but not to 0, converged to something other than 0, which means the series diverges. Make sense? Now, of course, why does this have to be true? Well, if you think about it, the items I'm checking out of my Walmart thing, beep, 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 every time. the items in this sequence that I'm adding up, they're all getting closer and closer to a half. So it's sort of like I'm scanning, beep, almost a half, beep, almost a half, beep, almost a half. And if I keep adding up almost a half every time, infinitely many times, I mean, obviously the total is going to get bigger and bigger and bigger and bigger and bigger. This thing has no choice but to diverge. Right? So if I just put my thumb over the sum and look at the sequence, k over 2k plus 1, that didn't go to 0, went to a half. That means that the series diverges. And again, it's super important now to keep track of the difference between sequence and series, right? So the series is my sequence all added up. And so how do I tell if the whole series, the whole sum, converges or diverges? Well, one way is to put my thumb over the sum and just look at the sequence that's left. If that sequence doesn't go to 0, then I know the original series, the whole sum, diverges. Okay? Here's another one. 3k to the fourth over k cubed minus 7. We look at that series. Well, if I take the limit of the sequence that I'm adding up, imagine putting your thumb over the sum and just look at the sequence that we're adding up. Those terms are all getting bigger and bigger and bigger, right? The k to the fourth beats the k cubed. And so what happens is this sequence that we're adding up keeps getting bigger and bigger. So I start adding bigger and bigger numbers every time, and there's no way I could pay for that at the Walmart, to stretch our analogy a little bit, right? The total keeps getting bigger and bigger and bigger as if I add bigger and bigger numbers every time. This whole thing diverges. Okay, let's try one more. Here's the sum of just 1 over k. Well, if I check, put my thumb over the sum, the limit of 1 over k, of course, that goes to 0, right? So this ought to tell us it converges, right? Wrong. Okay, so this is the place where the divergence test is so easily misunderstood and it's so easy to get into trouble. The divergence test for this one tells us nothing because the divergence test says if the limit of the sequence isn't 0, we diverge. In this case, the limit of the sequence was 0, and the divergence test is useless. Absolutely nothing we can say here. It doesn't go the other way. Just because the limit went to 0 doesn't tell us that the series has to converge. Another way of saying this is you can never, ever say that a series converges because of the divergence test. The divergence test doesn't work that way. It just looks at a series and says, hey, dude, you've got to diverge. Or it says, yeah, man, I don't know. Okay, those are the only two answers the divergence test can give you. Now, it's maybe the most important test because it's sort of the test I would always do first because it's really easy to do. You just look at the thing and check to see if the sequence that we're adding up converges to 0. If it doesn't, we're done. Okay? And even if it doesn't work, and it on the exam usually won't work, I mean, otherwise we wouldn't need any other tests, right? I mean, the divergence test is usually find ourselves in exactly this case, where the divergence test doesn't help us. But the process of thinking through whether the sequence converged to 0 or not will often help us figure out what other tests to try. Okay, but again, the most common mistake that people make on this next exam, and the exam that gets people in more the mistake that gets people in more trouble than anything else and loses people all the points on the question is if you ever catch yourself saying that a series converges because of the divergence test, then stop, erase it, because that's wrong. Okay, big flashing red light here, right? You can never, ever say a series converged because of the divergence test. I mean, never, right? This is a huge, big deal. Never, never. I really mean it. Okay? If you catch yourself writing that something converged because of the divergence test, then you've done it wrong. Okay? So what does the divergence test do? It gives you an easy way to test if something diverged. Okay? So you can check and see if that sequence doesn't go to 0, you know you diverge and you're done. But it can't ever tell you that a series converged. Okay, I hope I made that clear, that this is such a huge issue and it's super easy to get this one wrong. Okay, let's try the integral test, right? So we'll be able to do that series I just showed you with the integral test. Right? So the statement of the integral test looks a lot weirder than the test for the divergence test did. It says suppose that you had a function f of k, right? And that's exactly what the ak equals, right? And so f is this function which is positive and decreasing. The positive is maybe more important at this point than the decreasing, but both have to be there, right? Then both the series, the sum of the ak, and the improper integral from 1 to infinity of f of x dx, they either both converge or they both diverge. Okay, so, wow, that's a lot to digest. We'll break this down here. First thing to notice is the integral test, unlike the divergence test, right, can let you say that something converged, right? Because the way the divergence test works is it's just a quick check to see if it diverges or not. And so the answer will either be it diverges or try another test. Okay? For the integral test, what you get is, well, this improper integral that I can do because I remember how to do improper integrals from from the last round of material, right? I can test that improper integral and calculate it out and see whether it converged or not. And so that will tell me what the series does. So I could get an answer of converge or I could get an answer of diverge, right? Because they'll both do the same thing. So the integral test is really useful this way because it'll let us tell whether something converges or whether something diverges. We could get either answer from the test. Okay, so what's all this stuff about AK equals f of k or whatever? Here's what it really means. Take the k's and turn them into x's. Make it a function. That's what it really means. Then you've got a function with x's in it. If that function's positive, right? So this won't work if the function ever turns negative, okay? And it's decreasing, right? Then we just look at this improper integral. And we integrate out to infinity. Now, why in the world should that work? Well, remember, way back to the beginning of this course, what's an integral? Really, a definite integral really is you break things up into lots of little pieces, add up the pieces. Wait a minute, adding, that was a sum. We only ever added up finitely many pieces. We just let them all get smaller and smaller and smaller, right? Well, an integral is a lot like a sum, right? We're breaking things up into pieces and adding up the pieces. And so that's really exactly what's going on here. The sum, right, of infinitely many things, right, versus this integral that adds up all the way out to infinity, well, they ought to be related somehow, right? They ought to either both converge or both diverge. If the sum added up to something finite and the integral was way much bigger and was infinite, that wouldn't really make a lot of sense, right? Because the integral really is a kind of a sum. So this isn't a proof, it's more of an argument that this ought to make sense. But what happens is if you take that series, turn all the k's into x's and make it a function. If it's a positive decreasing function, so now it's decreasing and it stays positive, which is really important for the next several tests that we're going to have, you can figure out whether the series converges by looking at what the improper integral does. All right, this desperately needs an example. So we have the sum of 1 over k log of k. Okay? So my sequence I'm adding up is 1 over k log of k. The function I need to be looking at then is 1 over x log of x. Is that positive? Well, when x is big enough, right, then log will be positive, x will be positive. Yeah, we're good. Is it decreasing? Yeah, it's as the x gets bigger, obviously that's going to go to 0. You could prove to yourself it was decreasing by taking the derivative and showing the derivative was negative and all that sort of stuff, which we could if we wanted to, but usually checking to see that it's positive is super important. Seeing that it's decreasing is usually pretty easy to see that, oh yeah, it's got to be decreasing without having to fight through taking the derivatives. You can usually just look at it and tell. So then I need to look at this improper integral. I'm not going to write the integral from, say, 0 to infinity or 1 to infinity. I started this one at 3. Why did I do that? Well, remember that the log of 1 is 0. So if I had put 1 to infinity here, I'd actually have a different kind of improper integral. I have an asymptote. This thing has a vertical asymptote at 1 because the log of 1 is 0. So the point is, in the integral test, you just need to start far enough along so that the integral makes sense, right? So we'll start from 3. I could start from 2. I could start from pi. It doesn't really matter. I can start from 15. It's just that I need to get to the point where the integral actually makes sense and then integrate from there on out to infinity. So when I do that, how do I integrate 1 over x log of x? Well, mercifully, right, we do this at the beginning of the sectional series. So hopefully everybody remembers how to do an integral. You look at this one, and this one's screaming out for u substitution, right? We let u equal log of x. The du will be 1 over x dx, right? So then I can integrate from 3 to capital N, and I'll get 1 over u du, right? If I do this, I'll need to change limits of integration if I write them like that. So I'll just switch them around so that the 3 becomes log of 3 and the n becomes log of n, and I get 1 over u du. Well, you integrate 1 over u and you get log of u, log of absolute value of u. So the whole thing becomes log of absolute value of log of n plus minus log of absolute value of log of 3. Oh, wow, okay. There's a lot to that. But the important thing is I can easily tell whether this converges or not, because when n gets big, log of n gets big. And log of something big is big. So this whole thing goes off to infinity. Remember the Tower of Power, log is kind of pitiful, and log of log is even more pitiful, but it still goes off to infinity, even though it does it slowly. So this integral diverged, so that means that my original series diverges because of the integral test. Right? Now, it's worth pausing to think for just a second. Let's try the divergence test on this one now. Right? We know this integral diverged. Could I have done this with the divergence test? Well, no, because if I put my thumb over the sum and looked at the sequence, 1 over k log k, the sequence converges to 0. Because, of course, k log k, right, in the denominator makes this whole fraction go to 0. The sequence, the list, 1 over k log k goes to 0. Right? So the divergence test is absolutely no use here. On the other hand, I have the integral test. The integral test will tell me this guy diverges, right? But the divergence test was no use and didn't help me at all, right? But this is one of the things that makes this material tricky is I've said something converged and something else diverged a few different times on just this one screen, right? The sequence, 1 over k log k, converges to 0. The series diverged because of the integral test. And this is why it's so important to keep the idea of sequence and series separate. The sequence is going to 0. The series, what you get when you add it up, is diverging, just like the function 1 over x log of x is getting closer to 0. It has a horizontal asymptote at 0. But when I add up stuff, when I integrate, it diverges. And that's exactly the analogy to keep in mind here. Okay, so a few minutes ago we did 1 over k, and I really had this sort of freak out where I said, you try the divergence test on this one, put your thumb over the sum, 1 over k goes to 0, so the sequence converges to 0, which means the divergence test doesn't help. The divergence test doesn't help us if the sequence actually does converge to 0, only if it doesn't. Right? So the divergence test was no good here at all, but the integral test is obviously the thing to do, because if I change the k's into x's and I get the function 1 over x, that improper integral from 1 to infinity of 1 over x is really easy to do. Right? In fact, if you remember, we had a rule. This was maybe the first or second example we did in the video over improper integrals. When you turn this into an improper integral, you then integrate it by going from 1 to capital N of 1 over x dx. Let the n go off to infinity. You integrate 1 over x and get log of absolute value of x, which then we plug in the n and the 1, and as n goes off to infinity, this whole thing diverges. So this is a divergent improper integral. So what does that tell me about the series? It diverged by the integral test. Okay? So this is one reason why this is a really, really awesome series, because it's the one that you want to keep in mind so that you don't make the mistake that I've harped on about 15 million times now about the divergence test. Because if you try the divergence test on this series, you'd say the sequence is 1 over k. That sequence converges to 0. So then you'd be tempted to think, oh, then the whole series converges. But it doesn't. Even though 1 over k goes to 0, even though the function 1 over x is getting small and getting close to 0, the improper integral, and therefore the series, both diverge. Right? So this is such an important series that it actually has a name. Right? This guy has its own name. That doesn't happen very often, that a series gets a special name, but this one does. This one's called the harmonic series. Okay? So we'll often talk about the harmonic series, and we'll use this in other examples, and we'll use this to compare other things to this harmonic series. Okay, so why the name harmonic series? Well, if you wrote out this term by term, you get 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on. A half, a third, a fourth, a fifth, and so on. Why harmonic? Well, if you know anything about music and physics, then this sort of cutting things down, or a piece of string that's 1 unit of length, and then half, and then a third, and then a fourth. If you change the length of the string, you make the thing go up by an octave every time, and so this is related to music and frequencies and all sorts of cool stuff. Hence the name. Well, another super important, in fact, a whole family of series are what we call p-series. In fact, the harmonic series is just a p-series when the p is equal to 1. So a p-series is 1 over k to the p power. And The harmonic series is just the special p series when p is equal to 1. And this guy will converge if and only if the p is bigger than 1. How do I know that? Well, if you remember back to our video on improper integrals, I said that we have a super important example here. It's the integral of 1 over x to the p. In other words, exactly what you would get if you turned the k's into x's here and did the improper integral. And the rule was that that improper integral converged if and only if the p was bigger than 1. So 1 over k squared, that series converges. 1 over k to the third, that series converges. 1 over k to the 1/2, that series diverges, right? So P series are a whole family of series, and they will show up a whole lot over the next few videos because they give us a great example of things that are super easy to just look at and tell whether they converge or not. Okay, so it's worth maybe pausing for a second to sort of explain the ongoing theme for the next several lectures. Right? So what we're going to have are two things. First, we'll have a bunch of examples. So things like the P-series that we just saw, or the geometric series and the telescoping series from the last couple of lectures, those are examples. Those are things that we can look at, and we just have a way to figure out the answer. For any P series, we just look at the power. If the power there, the P, is bigger than 1, it converges. Otherwise, it diverges. Super easy. We'll build up our stock of these sort of examples. On the other hand, we'll have tests. So far we only have two, the divergence test and the integral test. By the time we're done, we'll have at least a dozen of these tests, depending on how you count them. So what will be tricky on the exam is, here's a series. Does it converge or diverge? Right? Maybe it's one of the examples. And so we just look at it and we know. If it's not, then maybe we have a test we can use to do it. Or maybe we can compare it to something that we know, which we'll talk about in the next lecture. The thing that makes it tricky is knowing, well, what all the examples are, what all the tests are, and which tests to use. Because oftentimes there'll be maybe 6 or 7 different tests that will work and give us an answer. Sometimes there may only be one test that works. In fact, the example we did at first with the integral test, 1 over k log k, of all the tests we have, the integral test is really the only one that will work for that one. So sometimes you run across a series that only one test will work for, and sometimes lots of them will. So the only way to pass this test, pardon my pun here, right? The only way to pass this the next exam is to have done so many homework problems and spent so much time practicing these that when you see a series that's been running around in the wild and I give it to you and say, does it converge or diverge? Then you've done so many of them that you go, oh, you know what? I bet I should use this test, or I bet this is this kind of an example, and I know exactly how to do it. So what makes this material really hard is just that you have to work really hard to practice these to get good at knowing how to work the problems.